Howdy, my name is Josh George, and in this presentation I'll be covering the analysis and prevention of ghost targets and FMCW radar systems. This talk is basically going to summarize my report and investigate how interference between radars creates ghost targets and how we can minimize them. So let's begin with why this matters. FMCW radars are pretty integral to modern sensing in autonomous vehicles, navigation, in defense. But as the number of radars increase, interference between them becomes basically inevitable. When two vehicles transmit similar chirps, their signals overlap and form false detections, which we call ghost targets. These ghosts appear as real objects, but they don't really exist. This image here illustrates two cars emitting overlapping radar beams. You can see the blue car here and the yellow car here, and they're both emitting these radar waves, but they create this red object in the middle, which doesn't really exist, and it's created by that overlap between the two radar systems. In automotive applications, that can actually lead to pretty dangerous actions from the controls, like braking for no reason or missing actual obstacles that exist. So as radar density grows exponentially in this populated area, so does the risk of ghost formation. Hardware-based solutions like randomized chirps or time-divided multiplexing can reduce interference, but they're not really scalable to the current population. And they'll end up cutting into bandwidth and other problems like that. That's why the research community is more focused on DSP or digital signal processing solutions, which are post-process of the received data and separate real targets from interference without actually changing the hardware within the vehicles. Recent work introduces a correlation-based compression method that performs this separation directly within the software. So ghost targets form when two or more FMCW radars operate near each other and their transmitted signals overlap. This equation right here shows how the received signal at radar A, combines reflections from its own transmitter and interference from another transmission radar B. Right here. This second term introduces an extra frequency component that doesn't correspond to any real object. In the range Doppler map here to the right, we can see these appear as false targets, offset in both range and velocity. Multipath reflections can make this even worse, since delayed echoes overlap with the direct return, adding extra ghosts actually to the display. So what can we do about this? Analytical models will help us predict how these ghost targets form and where they will appear in frequency space. This equation here shows that the difference between the two chirps, represented by the timing offset delta t, produces an interference frequency of delta f of t. This means that even a small timing offset can shift the ghost into an entirely different frequency band, and that's how we can actually predict and later mathematically suppress it. This figure over here shows the correlation between range Doppler maps over multiple sweeps. Real targets maintain consistent correlation from frame to frame, while ghost targets will fluctuate randomly, as you can see here. The algorithm compresses or filters out these low correlation components, effectively shrinking the ghost footprint in the radar data. So what are the trade-offs of this? One major benefit of this approach is that it can improve the radar's SNR. By removing incoherent ghost-related data, the range Doppler image becomes much clearer. However, this process isn't perfect. Tightening the compression too much can remove weak but real targets. So there's a kind of a balance between how aggressively you filter interference and how much of the original target you want to preserve. Finding that balance will be key for real-world automotive applications. Researchers validated these ideas using both lab and field experiments with multiple FMCW radars. When additional radars were introduced with smaller timing offsets, these ghost targets appeared exactly where the model predicted, which is good. This equation here describes the relationship between ghost density, d of g, and the proportionality it has with n, the number of interfering radars, and the ratio of Ti overlap time to TP, total chirp period. After applying the compression, the number of ghost targets dropped dramatically by nearly 80%, while real detections remained above a 95% accuracy. These findings confirm that the model not only predicts ghost locations, but that the compression can effectively suppress them and, in the end, keep the real data. The success of these suppression methods depend heavily on radar design parameters. Larger bandwidth improves range resolution, but also increases overlap, while shorter chirps boost update rate but raise timing sensitivity. Future systems can use cooperative radar networks, which means that vehicles they'll share timing data to prevent interference altogether. And another promising direction is also to use machine learning. Neural networks trained on radar data can learn to tell real targets from ghosts. These AI-based detectors oftentimes outperform traditional methods, but they will need large data sets and are still costly to implement. So in summary, ghost targets remain one of the most serious interference problems in these radars. Analyzing these models help us understand and predict where these false detections come from, while compression-based DSP techniques can remove them effectively without modifying hardware. So as radars become more common in autonomous systems, combining these algorithms with cooperative and machine learning approaches will be the key to maintaining reliable detection in dense environments. Thank you.